In May 2021, China's Zhurong Rover rolled onto the Martian surface in Utopia Planitia, a region scientists suspect once held an ancient ocean. Within months, its ground-penetrating radar detected something unexpected beneath the red dust. What it found challenges our understanding of how water shaped Mars billions of years ago. Before Zhurong's arrival, scientists had spent decades debating the geological history of Utopia Planitia. This massive impact basin, measuring approximately 3,300 kilometers in diameter, sits in Mars' northern lowlands, where elevation drops nearly 5 kilometers below the planet's mean surface level. In the early 2000s, data from NASA's Mars Global Surveyor and ESA's Mars Express suggested this depression might have held a vast ocean during the late Hesperian period, roughly 3 to 3.5 billion years ago, when Mars' atmosphere was thicker and temperatures potentially warmer. The ocean hypothesis pointed to features resembling ancient shorelines, with some researchers identifying two distinct coastal terraces at different elevations, suggesting the ocean level dropped over time. But competing interpretations propose these same features could be explained by volcanic resurfacing or the slow movement of ice-rich permafrost, especially given that current surface temperatures in Utopia Planitia average minus 63 degrees Celsius. The debate centered on a fundamental question. Did liquid water once pool here for millions of years, or were these deposits always frozen? Zhurong arrived as part of China's Tianwen-1 mission, which launched in July 2020 and entered Martian orbit in February 2021. Named after the Chinese god of fire, the rover touched down on May 15, 2021, making China only the second nation to successfully operate a rover on Mars. The landing site at 25.1 degrees north latitude, 109.9 degrees east longitude, placed Zhurong in the southern region of Utopia Planitia, specifically chosen for its relatively flat terrain and scientific interest regarding ancient water. The rover carried 6 scientific instruments, but its most revealing tool proved to be the Rover Penetrating Radar, or ROPER. This ground-penetrating radar system operated at 2 frequencies, 60 MHz for shallow subsurface scanning down to 3 meters, and 15 MHz for deeper penetration, reaching approximately 80 to 100 meters below the surface. Unlike orbital radar, which provides broad regional data, ROPER offered unprecedented ground-level resolution, allowing researchers to map subsurface layers with centimeter-scale precision as Zhurong traversed the terrain. Zhurong's primary subsurface investigation tool was the Rover Penetrating Radar, known as ROPER, operating in 2 channels with distinct capabilities. The low-frequency channel penetrated up to approximately 100 meters below the surface, though with lower resolution, while the high-frequency channel provided finer detail in the upper 10 to 20 meters, revealing structures with centimeter-scale precision. The technology operates by transmitting electromagnetic pulses into the ground. Reflections occur at boundaries where material properties change, whether between fine dust and coarse rock or between sedimentary layers of different composition. However, the instrument has inherent constraints. Radar signals cannot identify exact materials. They detect contrasts in electrical properties, not composition. Certain materials like conductive clays can scatter signals, limiting depth penetration, and surface roughness affects data quality. Despite these limitations, what ROPER revealed along Zhurong's 1,921-meter traverse would challenge existing models of Mars water history. Along Zhurong's traverse, which ran roughly perpendicular to regional topographic escarpments, the high-frequency radar revealed a remarkably uniform sedimentary layer in the shallow subsurface. This layer, measuring approximately 4 meters thick, maintained consistent properties across the entire 1,921-meter path, suggesting widespread deposition rather than localized processes. Below 10 meters depth, the radar detected multiple distinct interfaces with reflections indicating class-supported structures, fragments of rock embedded in finer material, with fragment sizes increasing progressively with depth. Between 10 and 35 meters, a particularly striking pattern emerged. Dipping reflectors tilted approximately 15 degrees upward toward the nearby escarpment, maintaining consistent thickness and continuity across the survey area. Deeper records extending beyond 80 meters showed smooth transitions between an upper, fine-grained unit and a lower, coarser unit, with no evidence of volcanic layering or the cross-bedding patterns typical of wind-deposited sediments. At the surface, Zhurong's cameras documented additional features: etched rocks with weathering patterns, pitted cones suggesting volatile interactions, and polygonal terrain, fracture networks often associated with thermal cycling or ice. The data patterns were clear and repeatable. What they represented, however, remained open to interpretation. Analyses published in 2025 and 2026 offered several interpretations of these subsurface structures. One hypothesis considered the dipping deposits as potential ancient coastal accumulations, possibly formed by wave action in a standing body of water during Mars' early Noachian period, roughly 4 billion years ago when atmospheric conditions may have been different. Under this model, the 15-degree dipping layers could represent beach-like sequences where sediments accumulated along shorelines, with material sorting by size as fragments settled, larger clasts dropping first in deeper water, finer material washing further inland. An alternative interpretation proposed episodic hydraulic sedimentation during the basin's infilling phase, with multiple flooding events depositing sediments in pulses rather than continuous pooling. Some researchers suggested the uniform 4-meter surface layer indicated a much later resurfacing event involving aqueous processes, potentially during the middle to late Amazonian period, approximately 750 million years ago, far more recent than previously thought possible for liquid water activity. Other models considered saline water interactions and water vapor cycling in the lowlands, where briny fluids with lower freezing points might have temporarily mobilized sediments under specific thermal conditions. Impact-related processes remained another possibility. The Utopia Basin's formation or subsequent large impacts could have melted subsurface ice, creating temporary fluid environments that redistributed materials before refreezing. Each interpretation fits portions of the data, but no single model explains all observed features conclusively. Critical constraints limit what these observations can demonstrate. The radar data recorded dielectric permittivity values consistently below 9 throughout the entire probed depth, values inconsistent with widespread liquid water or water-saturated sediments, which typically exhibit values above 15. Current surface temperatures in Utopia Planitia average around 220 Kelvin, or minus 53 degrees Celsius, conditions where neither pure liquid water nor common brines can remain stable without immediately freezing or sublimating. The absence of strong signal attenuation in the upper 100 meters further constrains the presence of conductive fluids, which would scatter or absorb radar waves, creating gaps in the data record that were not observed. These patterns do not confirm an ancient ocean existed in Utopia Planitia. alternative formation mechanisms remain viable. Large impact events can fracture and redistribute materials, creating layered structures without requiring water. Wind-driven processes over billions of years can sort sediments by size through repeated cycles of deposition and erosion. The dipping layers could represent impact-ejecta deposits, volcanic ash layers tilted by subsequent geological activity, or paraglacial features formed through freeze-thaw cycles involving ice rather than liquid water. Critically, while these subsurface conditions could theoretically have supported certain chemical processes if water was temporarily present in Mars' past, this discovery does not confirm the presence of biological organisms, past or present. The data indicates geological processes. What drove those processes, and whether they occurred rapidly or over extended periods, remains under investigation. Similar dipping sedimentary structures appear in terrestrial coastal and deltaic environments, where wave action and water flow sort materials by density and size, creating angled stratification. However, direct comparisons require caution. Martian gravity, at 38% of Earth's, affects settling rates and sediment transport differently. Mars's thin atmosphere, currently less than 1% of Earth's pressure, alters fluid dynamics and erosion patterns substantially. Elsewhere on Mars, NASA's Perseverance rover has documented comparable evidence. In Jezero Crater, approximately 3,700 kilometers south of Utopia Planitia, Perseverance identified deltaic fan deposits with sedimentary layers indicating ancient water transport, likely from rivers feeding into a crater lake during the Noachian period. Orbital missions provide broader regional context. NASA's Mars Reconnaissance Orbiter and ESA's Mars Express have mapped extensive units across the northern plains showing similar morphological characteristics, suggesting that processes affecting Utopia Planitia may have operated on basin-wide or even hemispheric scales. The Mars Odyssey mission's neutron spectrometer detected hydrogen signatures in the northern lowlands consistent with near-surface ice, supporting models of volatile-rich deposits beneath the dust. China's Tianwen-1 orbiter continues collecting complementary data, including high-resolution imagery and atmospheric measurements, which inform refined gravity field models used by multiple space agencies for mission planning. These findings contribute to a growing body of evidence suggesting Mars experienced regionally variable water activity, with some areas maintaining conditions for aqueous processes longer than others, though the exact timing, duration, and extent remain actively debated among researchers. Publications in Nature, the Proceedings of the National Academy of Sciences, and National Science Review presented these findings to the international research community in 2025 and 2026, prompting responses across space agencies. NASA's Mars exploration program noted the data aligned with ongoing efforts to understand regional water distribution patterns and began cross-referencing Zhurong's ground-based measurements with archived Mars Reconnaissance Orbiter radar soundings of adjacent terrain. The agency's Mars Sample Return Science Planning Group indicated that similar layered deposits in other regions could become priority targets for future sample collection, particularly where ground-penetrating radar might identify subsurface transitions warranting detailed analysis. ESA's Mars Express team initiated reanalysis of existing MARSIS radar data across the northern plains, comparing orbital measurements with Zhurong's higher-resolution ground observations to refine subsurface mapping techniques for future missions. The European Space Agency's ExoMars program, which aims to drill up to 2 meters into the Martian subsurface, noted that understanding layered deposits at Utopia Planitia could inform drilling site selection for detecting preserved organic chemistry at depth. China's National Space Administration continues operating the Tianwen-1 orbiter while planning Tianwen-3, a sample return mission proposed for the late 2020s, with scientific objectives including subsurface material collection informed by Zhurong's radar observations. The findings contributed to updated Mars climate evolution models, with research groups incorporating new constraints on the timing and distribution of potential late-stage water activity into simulations of atmospheric loss and surface modification. Discussions at international planetary science conferences emphasize the need for coordinated radar measurements across multiple landing sites to determine whether Utopia Planitia's subsurface architecture represents localized conditions or broader northern hemisphere patterns. These responses reflect a scientific community prioritizing ground truth measurements and intermission data validation, rather than drawing premature conclusions. Understanding the timing and distribution of water-related processes on Mars advances knowledge of planetary climate transitions, how worlds shift from potentially temperate conditions to frozen states over billions of years. These investigations provide constraints on volatile cycling across the solar system, revealing how water, ice, and atmospheric gases redistribute through geological time under different gravitational and thermal regimes. Mars serves as a natural laboratory for studying planetary surface evolution in the absence of plate tectonics, offering insights into how impact events, atmospheric pressure changes, and temperature variations shape terrain without the resurfacing mechanisms that continuously alter Earth. The question of whether liquid water persisted in localized regions during Mars' late Amazonian period, far more recently than previously thought possible, has implications for understanding how planetary environments transition between states, and whether such transitions occur uniformly or vary regionally. Ground truth measurements like those from Zhurong provide essential calibration for orbital remote sensing, allowing researchers to validate interpretation methods across decades of satellite data and improving confidence in mapping subsurface structures elsewhere on Mars and on other worlds. These findings inform mission planning priorities, helping agencies identify scientifically valuable landing sites where subsurface layering might preserve records of past environmental conditions, guide drilling depths for sample collection, and optimize instrument selection for future exploration. While these subsurface conditions could theoretically have supported certain chemical processes if water was temporarily present in Mars' past, this discovery does not confirm the presence of biological organisms. The scientific value lies in constraining Mars' environmental history, building a timeline of when, where, and under what conditions different geological processes operated, which ultimately contributes to understanding how rocky planets evolve and what factors determine their long-term habitability potential. Questions remain about the full extent and duration of these processes. Ongoing analysis of the data, combined with future missions, will continue to refine our understanding of Mars' geological record. The investigation persists. If you want to follow along as new findings emerge from Mars exploration, subscribe and turn on notifications. More discoveries are coming. The visuals in this video are educational illustrations based on scientific research, peer-reviewed studies, and official space agency publications. These visualizations are artistic interpretations intended to support public understanding.